Okay, well, I hope you can see that slide a little bit better than the previous video. But anyway, this is where we stopped. We're talking about the Weber fractions, as they say in German. So let's go to the next slide. Estimating magnitude. So one of the interesting things about when you're estimating the magnitude of any stimulus is that there's not a direct linear relationship between the intensity of the stimulus and the thing that you feel, right? Sometimes, as you increase the intensity, all of a sudden the stimulus becomes more and more, the magnitude becomes perceived as more and more, right? And then other times, as you increase the stimulus, the magnitude gets perceived, it's kind of flattened out, right? So no matter how much you increase it, you kind of hit a flat thing, a flat plateau. That's called response compression, right? So as you increase the intensity of a stimulus, the magnitude that you're perceiving gets lower and lower. Just at some point, it hits a ceiling, and no matter how much you increase it, it just doesn't look like it's getting any brighter or louder or whatever, right? Then the opposite is a response expansion. That is, you start off perceiving it in a linear fashion, but then all of a sudden you hit a certain level of the stimulus, and every little change in the intensity of stimulus causes huge changes in the perception in what you're feeling. Okay, so for example, here's this diagram here, this chart here shows an example of response compression and response expansion. All right, the green line that's running, the green dash line that's running from left to right in a very straight line is kind of our control line. Okay, and this is where we're estimating line length. Right, so we're saying yes, this line is longer than that line. So the longer that you make the line, right, the longer we say the line is, and that's a perfect example of a perfect straight line relationship. Uh, the line's not going to start. The lines aren't going to be feeling any shorter or longer. The longer or shorter we make them, right? They're gonna, or the longer they get, right? It's going to stay in a perfect straight line. That's kind of our control line, right? That's what you would expect if there's this one-to-one relationship between the stimulus intensity, what's being shot at you, and the magnitude, what you're perceiving. That's what you would expect would be this straight line. Instead, for a lot of stimuli, for example, for brightness, for light brightness, as the intensity increases, we perceive an increase in magnitude, but after a while, that light gets to our eyes kind of get washed out. The light gets to the point where no matter how much brighter you're making it, it doesn't seem to get that much brighter. We sort of hit a limit as to how much light brightness we can perceive, and that's response compression. Okay. Response expansion is what happens to you with electric shock, right? So if I were to give you some tiny little electric shocks, you'd feel them, you'd feel them. They'd start to hurt more and more. But after I hit a certain intensity, all of a sudden, small increases in that intensity would result in huge changes in perception of how much it hurt or the feeling of it, right? So look, for example, here at the difference between, say, 30 and 40. If we go from 30 and 40 units of electric shock, look at the increase in the perception. We go from about here, a magnitude estimate of 20, all the way to a magnitude estimate of 50. Whereas before we were just going from, say, you know, 0 to 2, 2 to 7 here. So there's a huge increase in how painful that stimulus feels, the electric shock feels, just with small increases in stimuli. And this is called response expansion. Okay, and different stimuli, it can exhibit either response expansion or response compression. Okay. Um, we can also, with regard to estimating magnitude, right? There's a very simple relationship between the intensity and the perceived magnitude. It's a power function, um, and you'll notice it's a power function because these two curves are shaped exactly the same. They're flipped over, right? This is a mirror image of this one here, but notice that they're shaped the same, right? And that shape is illustrated by this formula here. Power, the perceived magnitude P, is equal to a constant, some constant, times the stimulus intensity, right? And that stimulus intensity is taken to a power, the power, to the n, stimulus intensity to the power n, right? Um, and basically, what that's telling us is there's a direct relationship between how intense a stimulus is and how it's perceived, right? And that relationship can give us either response compression, where it goes up for a while, then it flattens out, or response expansion, where it starts out kind of slow and then quickly powers up. Um, the n part, the exponent, tells us about how the stimulus is perceived, right? So the n is going to give the whether the n is going to tell you whether it's response compression or response expansion, right? So if you have an exponent, if this n is less than 1, like zero point 0.5 or something like that, you're going to have response compression. So as the stimulus goes up, you're going to get less and less. If the n in the s to the n power is greater than 1, you're going to get response expansion. And the greater the n, the faster the expansion is going to be. Okay, so it's a pretty cool little rule that holds across a lot of different species and a lot of different stimuli. Um, another so thresholds and magnitudes are ways that we use to assess the capabilities of the sensory systems of different critters, right? So for us, for example, we've done 100 years of research already, more than 100 years of research on determining the thresholds and magnitudes that we can estimate of sight, sound, smell, taste, all those things. Um, you can go beyond that, right? Those relatively simple measures of a threshold and magnitude with phenomenological methods. Phenomenology is the study of phenomena, basically. So, for example, there are some phenomenological methods where people can be trained to focus on different aspects of a sensory experience, and those people can then be trained to sort of to tell you what the different components of the experience they're feeling at that moment. It's a very difficult thing to do. Um, Another way to assess sensory abilities is to do visual search. For example, searching for stimuli. So an observer will be looking for a particular stimulus inside of a visual field, right? So they'll be presented with a visual field with a lot of different stimuli in it, lots and lots of them, and their task is to find the stimulus that's the target stimulus, the thing that they're looking for. And what you do is you measure reaction time. So in other words, you present the stimulus to them, and then you count how many seconds it takes for them to find it, and then push a button and say, "Yeah, I found it." Okay. For example, people are really good at detecting faces inside of a scene, and we're going to talk about that later. It doesn't take us very long to detect a face in a scene, right? But if I were to tell you to look for, like a can or some inanimate object, it would take you a little bit longer to find that. There's different when you're measuring sensory responding in people. One of the things you have to take into account is different people respond to different ways to different stimuli. That's just the way it is. And so the research that we do in sensation and perception has to take that into account. For example, there's what you would call the liberal responder. It's somebody who's, like, I guess, kind of afraid that they're going to miss it. So what they do is they'll hit the button or say, "Yeah, I saw it," even if they're just barely sure or not really sure that they perceived something, they'll say they did, right? Um, each person has a certain response criterion. In other words, each person has a response bias, whether they tend to be liberal responders or more, or more careful about the way they're responding. One of the ways that we deal with these differences in baselines is through signal detection theory. Signal detection theory takes into account not only when somebody correctly identifies something or incorrectly identifies something, right? Um, Also takes into account false positives. That is, when they say there's something there and there isn't there, or when they completely miss it. So it's there and they don't see it, right? So the possibilities are it's there and you say it's there. It's not there and you say it's not there, right? It's there, but you say it's not there, or it's not there and you say it's there. Right? Those are the four possibilities, right? And signal detection theory can take all of those into account. Uh, False positives, false negatives, hits and misses, right? And use those when you measure all those things, not just if they found it or not. When you measure all those things, you're able to come up with a more complete picture of an individual's response profile. So for example, here we have two people, Julie and Regina, and their task was to see if they see a light flashing of different intensities. Um, and we're looking for the 50% threshold at which they say they saw something, right? So so what we do is and this is of course the absolute threshold we're trying to determine, right? The point at which they get the stimulus right 50% of the time, right? You would think that it would be the same for everybody, but it's not. In this case, it looks like Regina is. Uh, it looks like she's less sensitive to light, right? It looks like it takes more light. It takes a higher intensity of light, I should say, for her to perceive it. And Julie looks like it takes a lower perception of light, right? But in fact, it may simply but the question you want to ask is Julie really more sensitive to light than Regina, or is she a more liberal responder, right? So the way you would assess that is how many false positives did she have, right? You'd say how many, not only do we do this, right? We measure the times that they were able to detect it correctly, the different intensities, but you'd also measure how many times did Julie ring in when she shouldn't have rung in, right? If she rung in more times than Regina did, then we could say, yeah, well, she's not really more light sensitive. Rather, um, she simply is a more liberal responder than Regina is. And that's the end of that lecture.